All right. Good afternoon, everybody. Um, so I guess for today's class, I'm just going to just sort of continue a little bit off of last time's content. So one update one update we have the exam next week. So it's going to be on a Thursday of next week. So I'm guessing it's going to be on the 14th of October. I'll go ahead and I'll make an Canvas announcement that will sort of go over that. So for the exam format, I don't really plan on using the lockdown browser, only because the lockdown browser seems to sort of, first of all, it has issues in general. But second of all, for a class like this, a lockdown browser type exam, multiple choice questions and stuff like that seems to not really be a good idea for 477 algorithms. So, so I'm going to have it where the exam will be in a PDF form. So I'll probably have it sort of unlocked a few minutes before the exam. So it's going to be during our normal class times. So next Thursday at 1 to 15 p.m. around that time is when we'll have the exam. And it'll be a PDF. You have to download it. And of course, either you can, print it out and sort of write on paper, or you can have some paper, write it down, scan it, upload it to the submission area. You also could use like a writing pad or a tablet, but some form like that. Um, I can't really think of any better way of doing it other than that, because a lockdown browser for this type of exam seems kind of silly. I want you to sort of work out some of the problems, and it's more convenient to have an actual sort of to write it all out. I mean, of course, let me see, you could actually try to use sort of Microsoft Paint on your mouse and draw things out like that, but I think that's going to not really be very very much preferred. I think that'll be pretty much a bad idea. So that's going to be the format, and the exam questions will be similar to what's in the homework. So I guess the best way to prepare for the exam is go over the homework assignments, because I'm going to have stuff like that on the exam. So I may have you trace out the same type of algorithms like in the homework, but of course a different input, different list or different number will be used, but the same type of questions will be on the midterm. I could actually put some questions where devise an algorithm to solve this problem and what's the runtime going to be. I think I have a question had a question like that on one of our assignments where think of an algorithm that takes O of log n time that will do this particular task. So that could also be on the exam. So really the homework questions are really going to be a good sort of help for that. So I guess I could have a study guide sort of put together and have it up by before class on Thursday, and spend time and go over some of the answers on the homework just to kind of go over those with you. So that'll be kind of like my way of doing the exam review. Go over the solutions and go over how the solutions come out if in case you had some issues getting the correct answer, and so forth. So yeah, it's going to be basically the exam. So don't think it should be anything too drastic, nothing too bad really. But that's going to be the format for the exam. And on Thursday, I'll go over a review. It could be a shorter class because it might not be too much review unless there's questions, and unless maybe I may go over the examples kind of fresh, work them out right. That could actually just post the answers as well, but yeah, sort of go over it fresh so you can kind of see how I work them out. So maybe it kind of is a better learning mechanism, but we'll see. So it could be a shorter day, but I'll see how I do the exam review. So that's pretty much the only really update for right now. And of course, the homework, well, the recent one is due this Friday. Now, I know you didn't really have you don't really have the solutions for the homework. You're not going to get them graded by now, by, the exam possibly. But I could sort of give you I could post solutions for the radix sort and bucket sort up on Canvas. So you have the answers to them. So if you don't get your feedback by the exam, at least you'll know what the answers are. So at least you'll know how to work those problems out, because you'll have those kind of questions on the midterm. So, all right then. So I think that's sort of that sort of goes over that midterm announcement. Let's go ahead now and go into our next next topic for the class. So I'm going to do a screen share. So, okay, so let's go ahead and open up OneNote. So, I guess the other day I was going over red-black trees and AVL trees, which are sort of two different types of sort of search structures. And we're going to now create a more sophisticated, or not create, but really define a more sophisticated data structure that's also going to be a search structure as well. Let's go ahead and talk about that structure. Known as B trees. B trees. I don't know how I got the name B trees, but that's the actual technical term for it, B trees. I'm going to call it a B tree. So, well, it's going to be basically a search structure. It's going to be a search structure, and it's going to be also a tree type structure. So it's going to be a balanced search tree. So we went over ABL trees and red-black trees. I'm not going to really go over into those too specifically, but those are just two sort of balanced sort of search tree structures. So okay, fine. And those ones had a trade-off, whereas really the main trade-off was that ABL trees are a little bit more better in terms of their height. Red-black trees aren't as efficient, I guess, in terms of height. And also, red-black trees has the one benefit where every single node you only have to store a 0 or 1, red and black, instead of storing the actual height of that node. So there's some benefits like that. Um, so anyway, so anyway, um, so for B tree, the same sort of concept, except it's going to be some modification to this. So it's going to be really just a method of really, it's mostly used for, I guess this is actually from the book. I'll go ahead and write this down. Optimized um, for disk I/O. And the main one's going to be and relational databases, maybe even all databases actually. I'm not sure about sort of NoSQL and MongoDB and all that. But the idea is that this approach is a little better for stuff like database because, okay, so the idea for a B tree is that each node contains a set of different keys, not just only for one key. So AVL tree, red-black tree, each node has one key, which is good enough. But if you want to retrieve many keys, for example, well, a B tree is a better idea because a B tree, each node contains an array of different keys. Now, the array is going to be much smaller than the size of the list or size of all the elements in your structure. So having an array involves doing some linear type searching possibly, but each sort of chunk, each sort of node will contain not so many elements with respect to the size of the complete structure. So I guess I'll go ahead and I'll put this here. So we're going to have where each node maintains array of keys and pointers. Now, for the examples we'll do in class, they'll be relatively small, but in general, they could have a lot of elements, could be contained in every single node. But that a lot of elements is still small with respect to the complete input size, or in this case, n is the complete number of elements. It's going to be much less than m is the key, really. So, okay, so the idea here is that it's sort of a benefit of retrieving. So for an AVL tree or binary search tree or red-black tree, if I want to retrieve multiple items, I have to restart a new search over and over again for every single key. Whereas this situation, we're going to maintain sort of each node, so each node slash level maintains keys in sorted order. Now, that's not the most important part, but that could be some optimization. But the idea is that because of this, we have everything structured nicely. But if I want to retrieve many different keys at one time, so each sort of node maintains sort of keys that are kind of close to it, which whatever that means close to, or close in terms of its sorted order. So if I want to retrieve many keys, I'll have to restart a new search over again every single time. The idea is that it may have some elements near each other in that node. So if I want to retrieve multiple keys, just traverse all the nodes in that, all the keys in that node instead of having to do a new search again. That's the whole idea. So when we do an example, it'll make more sense then. So basically, all the leaves in a B tree, all the leaves will be at the same level. So that's nice because that way a tree will be relatively balanced. It's going to be a very balanced structure. So that's the whole idea with this. And basically the idea is we have the following. So we have different B trees at different degrees. So a B tree can have a degree. Degree T. I don't know why they use T in the book. So T means that that's how many possible children it can have. So it has degree T with T minus 1 keys. I think that's the idea. Or I'm not sure if I forgot if in the book they use T for number of keys, then you have T plus 1 sort of pointers, or if you have a degree T and T minus 1 keys. But the idea is that we're going to have several pointers and we're going to have T minus 1 number of keys. So you have one less key than pointers essentially. So now the most basic sort of B tree we're going to go over, the most basic tree is a 2-3 tree. And there's also a 2-3-4 tree as well, but I'll stick to a 2-3 tree for right now since it's a pretty simple structure. So for a 2-3 tree, what that means is that we're going to have, so each node um, contains at most 2 keys and at most 3 children. Obviously, this doesn't include the root. So root has no children, but has at least at most 2. But the idea is, except for, so this I'll put this here right here. So each node contains at least 1 key and at least 2 children. Obviously, except for the leaves, but for any other node, that's going to be the idea. So we already can see right here it's going to be balanced because every single node has at least 2 children, except for a leaf, which means that it's going to be at least as the same level, same sort of level as a balanced binary tree. Now, if you have more children, then it will contain more elements every level, so it's going to be better than a binary tree, but it's going to be at least as good as a binary tree. So there's no way we restrict it where there's no way we'll have only one child ever. That's the whole idea. So this is sort of what we're going to be doing here. So let's go ahead and first draw up an example B tree, and then I'll go over how we do a search on a B tree, and of course, then we'll go over how to do insertion and deletion from a B tree. Let me go ahead and draw an example. I'm going to try to draw the example here, but it's definitely a little bit tough to make sure the example does look okay. Go ahead and just sort of here. I'll put this in front of me so I don't mess this up. So we're going to have the following. So let me just using the shape so my little is this way. Separate these nodes over. It actually comes out decently. I'll have two over here. Yeah, it's gonna be a little bit not so smooth, but good enough. Yes. These blocks over here, they're going to just be nodes in our B tree. So have the following. So every node contains at most two items. So we are. Right, don't mess this up. $17. But let's see. Well, 20. I'm over here. Something I think. So okay, I'll just do it. So then we'll have 6, 10. I'm missing one block. Let's put one here. So lopsided. Let's try this again. Better. Let's see if this is valid. I kind of drew this up kind of randomly. But this is going to be example B tree. I think this should be correct. Okay, so we'll of course go over how to construct it, but this is going to be example B tree. So each block is going to be a node and it has at most two keys and at most 3 pointers. So the idea, if I want to find something in our B tree, is very similar to doing a binary search tree sort of traversal. So let's say, for example, I want to find 5 in my B tree. If I start from the root level, and the first key is 20, 5 is less than our first key, so it has to be somewhere on the left side of 20, somewhere over there. Looking at this element here is 15, well 5 is somewhere, it has to be to the left of 15, so that means 5 would have to be somewhere in this node. And we see the very first element contains 5, so we found our 5. So let's go ahead and let's also try for find 10. The same idea, we first compared 10 to the first element, 20. 10 is smaller, so 10 has to be on the left side of 20. And here we have is 15 in this element. And since 10 is less than 15, then 10 has to be somewhere in this node over here. For this point, we'd have to linear search through this block. Now we have 2 elements, so it's not too bad. But if we had like a B tree where we had more elements in each node, we have to linear search to find it. Now, linear search is not so fast, but because each node does not contain a lot of data, even if let's say it has like 100 elements, let's say for example, yeah, if you have that big element sort of node, that means the B tree is probably going to have a lot of elements, way more than 100. So that 100 element linear search is not going to make a big impact if, let's say, the number of elements in your list is 1 trillion or something along those lines. So that's kind of how this works. Let's go ahead and try other searches. So let's try to find 17, see how does that work. So 17, look at the root level. 17 is less than our first element 20, so it has to be on the left side somewhere. Then 17 is larger than 15, so it has to be to the right of 15, so 17 has to be somewhere in this um, node, which is right there. So let's go ahead and now try to do a find on 35. So 35 is going to be larger than 20, but less than 40. So that middle, so this pointer is going to be used to help us find 35 because it's not less than 20, not larger than 40, it's in between the two, so it has to be somewhere in this middle subtree. Jump over here and look at 30. Well, 35 is larger than 30, so 35 has to be on the right side of this tree, like that. If I look for, let's say, I want to find 70, we start from here, check, 70 is bigger than 20 and bigger than 40, so it has to be, you have to follow this point we have to take. We jump over here, we see that 55, well, it's 70 is larger than that. The next element is 70, so we found it. If it was between, let's say, the elements in between the two, we pick that middle pointer. If it's less or larger, we take the outside pointers, if that makes any sense. That's what we use to actually find it. So very similar to a binary search tree search, except we have to sort of loop through the keys in that node until either find it or we find that, well, between two keys, it has to be somewhere in between, so you have to take that pointer. So for example, like, I mean, even 25, for example. So we have 20 and we have 40 at the root level. So 25 is in between these two, so it has to be in this middle pointer we have to take, which is sort of a pointer that's between those two keys, basically. So that's really the method of doing a find operation. So very similar to a binary search tree, except maybe a little bit different. So that's how we perform different types of searches. So the nodes, the keys are anywhere in our tree, but the idea is that the leaves are going to be always at the same level no matter what. So let's go ahead now and go over how do we actually construct a B tree. Let's go over insertion. So we insert into a B tree. So the idea, just like for a binary search tree, we have to find the location of where the new key should go. So that's our first step. So it's just like basically doing any type of binary search tree. Search tree, you have to find the location for it. So we're going to, of course, insert the new key somewhere, actually, new key at the leaf level. So just like with a regular binary search tree insertion or AVL tree insertion or whatnot, same concept, we have to basically do this search and insert something at the leaf level. And then we have to do is if the node where the key belongs has a vacancy, well, then just simply insert the key into this vacancy. But of course, you want to maintain, so you want to insert it or insert key such that sorted order is maintained. We have to make sure that all the keys are always going to be sorted in each node. Now, if there's no vacancy possible, so if there is vacancy, then we have to split the node, split that leaf node, split the leaf node, and pass the, I guess the median element, I guess we can say, in this case, the median up to the parent. And then it's going to recursively do the exact same work as we did at leaf level. We pass the median or the middle element up to the parent, and then it will try to see if it can fit that into some element in the parent. If it can't, it has to split that as well and keep doing this all the way up to the root level. And potentially have to split the root as well and make another root. So basically, each splitting action is constant time, but in the worst case, we have to carry this all the way up to the root. It's kind of hard to really explain it without doing an example, but that's the idea for insertion. So let's go ahead and sort of do some examples how to actually construct it. So, but I guess I'll maybe put some notes here. Then and recursively perform same work on the parent. So anyway, let's go ahead and just go over inserting into our B tree, and then let's just sort of go with that. So let's first go over inserting. So on insert 36 first. So we have an empty tree. So pretty simple it's going to be. I'll just use a box this time like this. So essentially we just have our root node and we have 36 right there. This will be our root and our leaf at the same time. Nothing too hard there. Let's go ahead and now continue. Let's now insert 24. So I will actually go ahead and just copy this instead of writing this whole thing out. So I'm going to go ahead and insert 24. So 24 less than 36. So 24 has to go to the left of 36, and I guess we found the vacant spot. We know that 24 has to go into this node. So we're going to scoot 36 over to the right. Insert 24 right there. So our root / leaf node contains those two elements. Nothing too bad just yet. Now let's go ahead and insert, I guess you can say 88. I'll insert 88 next. I'm actually going to maybe just actually copy this block several times. I'm going to go ahead and just copy this so I can reuse this. I'm going to go ahead and actually trace this part out. Just copy this empty block several times. This will be nice. Okay, so let's go ahead now and insert 88 next. Insert 88. So right now we're going to have 24 and 36 is going to be first, is in this B tree. So 88 is going to be larger than 24 and larger than 36. So 88 would have to go to the right of 36. But this tree or this node is actually filled up. We can't insert 88 into this node. So what we're going to do is we're going to have to split this node basically, because 88 is a problem. I'll put this here in red just to kind of denote that 88 is the issue. So to do this now, what's going to happen is, well, between these three elements, 36 is actually going to be the median. So return at 36 up to the parent, and the parent is empty, so we're going to go ahead and create a new root in this situation. So the new tree looks like this. Sort of move this a little bit. Good. So we're gonna have 36 right there. Actually, we're not on mistake. So we actually have to so we take 24 and 36. So this node, sorry, we're gonna split this node into two pieces. My mistake. So we split into two pieces, such. And we're gonna have 24 over here and 88 over there. So we have these three elements. We split to the node in two pieces. One will have 24, one has 88, and 36, which is the median, is returned up to the parent. The parent here is empty, so is it going to be a new root? We have 36. That's going to be the result. I'll zoom out so you can see all this. So what we did basically was, well, we wanted to insert 88, and it couldn't fit in that node. So we have these three elements. We're going to split those two nodes, 24 and 36, or those two nodes are going to get split. And then the median, so the median of 24, 36, and 88 is 36. It gets returned up to the parent, and we split them into two pieces. We have 24 and 88, and the parent will be 36 among these. So we just had to split 24. We had to split this node basically into two smaller nodes over here and over here. And then the median was returned up, basically, to the parent, and that's going to have its pointer set up to point to those two children. So that was a result of inserting 88. So any issues on that? We'll do some more insertions, obviously, to practice a bit more, but sort of a bizarre, kind of a bizarre structure, but it is nice because this is the way how it maintains that balance. So let's go ahead and take this existing tree. Let's insert 75 now. Let's do several more insertions to get more practice with this. So I might do even more in my notes because if you want to practice this a lot more, I'm going to now insert, let's insert 75. And I'll redraw this tree over here. So I'm going to just move this like that. I'm going to move these around a bit. Put it here. I'm going to go ahead and sort of take these two. So this is a bad idea. It actually worked out pretty well. Look, it actually worked out nicely. Wasn't too bad. Okay, so we have this same B tree. Or we have 24 over here, 88 over there, and 36 right there. Okay, let's insert 75. So from the very top level, 36, 75 is larger than 36, so it has to be inserted to the right of 36, which is going to be somewhere in this node over there. And we see here we have a vacancy, so you have to sort of scoot 88 over to the right, and then have 75 inserted to the left of it. So we scoot 88 over, have 75 right there. So it's always nice, but you don't have to actually split the nodes. If let's say we have a vacant spot, we just sort of insert it and we have to scoot elements over. It's like that basic insertion. So for insertion sort, that insertion loop, we're doing that basically to sort of fit this element into the right spot pretty much. So anyway, that's the result after inserting 75. Let's go ahead now and let's insert our next node. Let's go ahead and insert 22 next. Insert 22. So we're here. This. Let's take our existing tree. We have 36, 75, and 88. Okay, so insert 22. And this will not really cause any potential problems because once again, 22 less than 36. So then 22 has to go somewhere over here. And we have a vacant spot, so we're going to sort of scoot 24 over to the right and make room for 22 to be inserted. So no issues there. So now we're going to probably have an issue coming up soon. So yep, let's go ahead and now insert 19 into this B tree. To insert next. So here's our existing tree. 2, 7, 5, and 8. Let's now insert 36. Oh, sorry, 36 right there. Let's insert 19. Okay, so 19 is less than 36, so it has to be on the left side of 36. And we see here we have a leaf node. So 19 would have to go over here into this leaf, but the problem is, well, we don't have room for 19 to be inserted. So what happens now is we're going to have to split this node. So we have the median, which is going to be 22, that gets returned up to the parent, which the parent is going to be this node right there is the parent. Return 22 up to that parent, and we're going to split this into two pieces. 19 and 24 get split, and the root gets, or the median is returned up to the parent. Let's go ahead and sort of map this out. So I'm going to So, this. So this part is not going to be adjusted at all. It's going to be the same content. So we essentially had to split 19 and 24 into two nodes. And then 22 is returned up to the parent, which is right here. So we have to scoot the parent element over and insert 22 right there. That's going to be the result. We go ahead and sort of zoom out so we can see all this. So a 19 had to be inserted. Well, that caused a problem for that leftmost leaf node. We could insert 19 over there. So we had to go ahead and split that node into two pieces and return the median of that up to the parent. So we had 19, 22, 24. So 22 is the median, and we first have to split this node into two pieces, 19 and 24, which we sort of took this node and split it into these two nodes right there. Return 22 up to the parent. So the parent has 36. So we have to insert 22 there. And since the parent does have a vacant spot, we could actually simply scoot 36 over, make room for 22 to be inserted. And then we have to create a new pointer because this involves creating a new, we split this node into two nodes. So we have to create a new pointer, which we have to, so the code for this is a little bit, confusing. We have to store these two pointers and assign them to the parents like that. But this is going to be the result after inserting 19. We have to do a split over here. I mean, I'll put this node here. Split. I think also right over here as well. It's here too. I have to split this node. All right. So any issues so far with this B tree? Making mistakes, that's good. Let's do some more insertions. So I'm going to just sort of follow my nodes. Let's insert 11 next, which is not going to cause any potential issues. I'll zoom in on this a little bit. So here's a little bit zoom in. Let's now insert 11. I'm just trying to get this sort of tree kind of somewhat filled up. I guess I can insert something to the right, but I'll just insert 11 since I want to follow my nodes so I don't make a mistake here. So in this situation, well, we're going to have the following trees. We have that root, leaves, two 36, 24, 75, and 88. That inserting 11, well, that's going to cause not much of an issue either. So what's going to happen is 11 is less than 22. So as we traverse through the root, we have to see it as less than 22, so we have to insert 11 to the left of 22. And the left of 22 contains this node right over there. And right there we have a vacant spot. It's a leaf node clearly, and have a vacant spot available. So we just simply scoot 19 over and make room for 11 to be inserted. So it's always nice when we don't have to do any type of extra work, just simply scoot an element over. So now I'm going to just basically insert 25 next to try to cause some mayhem. Go ahead and I'll just copy this tree again. So we have 4. This. All right. 11, 19, 24, 75, 88, and we have 22 and 36. Okay. Here's our current B tree. And I want to now insert 25. So in this situation, 25, to start from the root, well, 25 is larger than 22, but less than 36. So that middle pointer is going to be used to insert 25. We jump to the middle, and this node right there is definitely a leaf node, and it does have a vacant spot, so we're going to have to just go ahead and insert 25 into correct sorted position. So, again, nothing too drastic over there. Yeah, did I miss something? Oh, okay, fine. So I insert 25 right there, and now I'm going to insert 30, which is going to cause a little bit of mayhem in this tree. Let's insert 30 next. So I'm going to just, okay, I'll just go ahead and I'll just paste these blocks over here. That, and I'll just draw the arrows in. Right. Now we're going to have 22, 6, 11, 13, 24, 25, 75, and 88. All right, so we insert 30. So once again, so 30 is going to be, well, it's larger than 22, but less than 36. So you have to follow this pointer to go to that middle node over here. And we see that this middle node is a leaf node, so we insert 30 right there. And we see here, well, we have a problem because we really can't insert 30 right there. So in this situation, we see that 25 is going to be the median of these three elements. We return 25 up. We're going to have to split this node because we can't make room to insert 30 into this node. So let's go ahead and work with this. Let's see what we do next. So what's going to happen right here is at the very bottommost level, which I'll just draw way down over here. We're going to have 4 nodes now. We're going to have 11, 15. And we're going to split this middle node, so 24 and 25. This will get split into two nodes, 24 and 30, and 75, 88. So all I did was so far, so we're going to zoom out a little further so we can see all of this. We simply did at this leaf level, we just simply split this, so 24 and 30, and then 25 returned up to the parent. Okay, let's go ahead and copy the parent node there. We have 22, 36, and then 30 was returned up at this level. And this also causes a problem because a parent is not able to handle a 30 because we already have a full node. So what happens here is that, well, we're going to have to split this as well into two nodes and return the median, or 30, up to the parent. So we're going to actually create a new root node because this root will get split and it creates a new root above it. So let's go ahead and work this out. Let's go ahead and redraw this now to sort of summarize all this. So at the relief level, we still have 11. Oops, we still have 11 over here. 11, 19, 4, 30, 75, and 8. Now this will get split. So we're going to have 22 and 36. So we're going to have 22, and we're going to have 36, and these will point to these two nodes, like that. And then returns 30 up to the parent. A new root is going to get created. Has 30 over here, just like that. All right, zoom out all of this so we can see everything. Here's two zoomed out. So anyway, what happened at the very bottommost level, we had first inserted 30, and we couldn't really deal with that because we had a full node over here. So we had to split this into two nodes, 25 and 30, and 24 and 30, and 25, which was the, oh, wait. 20, actually, no, never mind, that's fine because 25 is returned up. Yeah, so I think I made a mistake. 25 is supposed to be returned up. My mistake. I guess I must have messed this up. 24, 30, and 25 was returned. And then this couldn't work, so 25 returned back up here. So my mistake. So what happened was we have 24, 25, 30 was going to get inserted. Can't fit 30 there. So 24 and 30 split, return the median 25 up to the parent. And then we had 22, 25, 36 at the parent level. And that also wasn't actually going to work because we have too many nodes, too many keys at that node. So you have to split this into two pieces, 22 and 36, and 25 is returned up. So it should be like this, actually. So we had to do the splitting up the tree like this. We first had to split this node, which returns the median up to the parent, which caused the parent to also split, and it created a new root node. So I missed that as well. And then that was the result. So we have these steps we had to follow. So every time we basically insert into a node, if it's full, we split it by the two ends, and the middle elements return up to the parent. And if the parent can handle it, we just insert it to the parent level, and we're done. If not, we had to split the parent also, return the median up to its parent, until we finally hit, in the worst case, up to the root level. As we can see here. Split these two, turn it up here, split these two, return a new, create a new root node. And now we're back to a regular B tree. Everything is all fine. Everything is in order. And there's our new B tree just right there. So Yeah, so imagine trying to code this is definitely a little bit of a pain. So anyway, that's after a few insertions. I mean, so I have any more notes on insertions? I do have, let me see, I have notes on this. Well, actually, I don't have any further notes. This was kind of like the sort of covers all the cases really. So any questions or issues or any confusion on any of this? This is definitely a confusing structure in my opinion, but it does work out like that. So really, the idea is that inserting takes sort of the height of the tree number of steps, and then to insert into each node is constant time, and the splitting actions is also a constant operation. And we always delegate to the parent every single time. So if we have a full node, we split that into two pieces, return a median up to the parent, and if the parent can handle it, we insert into the parent element into that key somewhere, and we're done. If let's say the parent can't handle, we had to split the parent into two pieces and then return up to its parent and so forth. That's really the whole trick to B trees, basically. So anyway, let's go ahead and sort of do some more notes on this, but that was just the basics of insertion. So I could insert some more elements. So I insert, let's say, I guess I could insert, maybe do one more insertion, I guess, just to get a little more practice, I suppose. Let's insert 15 next. Let's insert actually two more that's going to cause a few more splitting, just so we can practice with more of that. So let's go ahead and insert 15 next. Insert. I'm going to go ahead and just sort of copy this now since I'm not going to be doing too much else. So I'll go ahead and copy the entire tree so I don't have to write the whole thing out. Okay. So to insert 15, what's going to happen is, well, once again, we start from the root level right here, 25. 15 is less than that, so you have to jump to the left side over here. And 15 is less than 22, so it would have to go somewhere into this node as you follow the sort of the path. And we see here that once again, this node is again filled up, so we have to split this node because if we insert 15 over here, we have 11, 15, and 19. So there's three elements to be inserted here, which it won't work. So we're going to have to again split this node and return 15 up to the parent. So to do this, let me go ahead and actually just, again, just copy and paste this, and I'll modify it so it'll be a little faster. So what happens here is we're going to just split that into two. So I'm going to go ahead and just copy this just twice. Okay. What's going to happen now is we have these two nodes, so 11 and 19, get split. Return 15 up. So we're going to scoot 22 over for 15 to be inserted. And we're going to have the following. Is our resolving tree. So all we had to do, let me just go ahead and try to zoom this down a little. So we found that 15 goes into 11 and 19 node, and it couldn't work, so we had to split 11 and 19, return the median, 15 up to the parent, and the parent had 22, so we had to basically scoot 22 over, put 15 there, and sort of modify the pointers accordingly, is the result. So of course, if we were to code this, it'd be more systematic than this, but that's sort of the idea, essentially. So 22, the pointers, so these two pointers essentially had to move also. So this had to also scoot over here. This had to scoot also as well to the left, and then the new left pointer pointed to 11 like that. So you have to do some pointer scooting as well, but I don't want to go over all that and sort of make this too confusing. But anyway, that's the result. And likewise, if I want to insert 80 into this tree, I'll do one more example. So we'll do another example with splitting once more. I'll go ahead and just copy this entire tree so I don't have to redraw all of that. Let's go ahead and insert 80 next. Okay. So in this situation, we have that we first check 80 with the top element, and it contains 25, so 80 has to be bigger. So we check the other pointer, the right pointer of 25, go over here to this node, check here, 80 is bigger than 36. You have to go to the right of 36, and over here we have a leaf node, and it's actually a full node, and 80 in fact would go right over there in between these two. And we have a problem again because we have too many nodes over here. So we're going to have to split this node. So we're going to have 75 and 80 will be split, and 80 is returned up to the parent. So let's go ahead and just exactly that, and then we'll be done with this example. This all out. So we have 75 and 80. So I should over here return 80 up to the parent. So I'm going to just copy this box. So we have these two nodes. We have 75 and 88. Turn 80 up over here. And then this is going to, basically we have this picture. Simply split that into two nodes, so turned 80 up. And the parent had a vacant spot for 80 to be inserted. And then we inserted 80 over there, and then we added this pointer to point to that 88 node. So that's sort of the idea. So a few more insertion examples. So yeah, so really the same systematic work. If there's a vacant spot, we put it there. If not, we split, return the median up to the parent, and the parent will go ahead and take care of all that problems basically. And we keep going further up. And the worst case scenario, we have to also split the root as well. So that's basically how all this works. So let's go ahead and go over some runtime analysis with this. And then I probably won't cover deletion today, as also as other kind of fun example with deletion, its own sort of problem. Let's go ahead and just not worry about deletion just yet. This. Okay. So the idea is that since each node, except for the leaves, has at least 2 children, the height is O of log n. The height could be better. Let's say if every single node has 3 children, which could also happen, the height could be actually a little bit smaller. It could be a better height in that case, but still asymptotically the same as log 2 of n, just like that. So basically, I won't really, this will be kind of more for exercise, but what's the minimal number of keys we can store with a height of age? What's the max number of keys we can store? So we have sort of 2 extremes. We have at least 2 nodes per 2 pointers per node, and at most 3 per node. So we can go ahead and figure out, well, how many possible nodes can we have for a given tree? and we have sort of the worst and the best case scenarios. So this is more for exercise for maybe for homework assignment or whatnot, but I guess I'll kind of formulate that a little later on. And basically, the insertion time, well, insertion runtime, well, we have to first find the location of where the new key should go. Well, it's going to be obviously O of log n time to do that, because the highest will always be logarithmic for a B tree. And then, of course, inserting into the leaf node, it takes O of 1 time. So O of 1, so constant time. Because even though it requires a loop, potentially, let's say if you have more than 2 keys per node, as we have 10 keys per node. So the whole point of a B tree is that the number of keys in every node is going to be quite large. It won't be only 2. I use 2 for the example, so it's easier to kind of trace these out. But in practice, the number of keys will be much more than 2. But the idea is that the number of keys in every node is going to be much smaller than the size of the entire of the entire structure. So even though we may have to loop through 100 elements, maybe even, yeah, but that amount of iteration is much less. So 100 is a constant compared to the actual size of n. So inserting, even though it requires a linear type of loop, it's constant because the number of elements we're going to cycle through is not going to be n or even a fraction of n. It's going to be just some constant. So it's going to be constant time to insert into that leaf. Now, if we have to split the node, so if the node must be split, well, that operation also takes O of 1 time. However, though, the split sort of, I guess, we may need to also split every parent up to the root node in this case. So each sort of operation, we split a node into 2 nodes. That's constant, but it gets delegated up to the parents accordingly. So in the worst case, we have to do this splitting O of log n time. So would need to split O of log n number of times. So that really means the overall runtime for insertion is going to take O of log n. Thus, time insertion takes O of log n as well. If every split action takes constant time, we have to keep doing this up to the root, which is going to be log n, because the height of this tree will be log n. So we do an extra plus log n work we do. So we first find the location where we have to insert our key. And we have to also split up to the root. So we're going to have log n plus log n, which is still going to be O of log n. So insertion takes O of log n time. So that's sort of the idea with a B tree. Let me go ahead and just sort of talk a little bit more about this. And then next time we'll go ahead and go over deletion. Now, one thing is that I want to go over the what's it called? The midterm review on Thursday. So you have a week to prepare for the midterm. So I'll have the study guide up and midterm as well. So study guide and review on Thursday. And next Thursday is our midterm. But then next week, Tuesday, I have another faculty senate meeting I have to attend. So in that case, I'm going to have to upload a video, but I'm not sure how to upload video to WebEx. So I may have to upload a video to YouTube, which is really weird. So suddenly it's WebEx, recordings. Now it records to WebEx, doesn't save onto my desktop anymore. So I may have to make a pre-recorded video for Tuesday's class. I won't be able to have class. I won't be here in person. I'll be at school at the probably Senate meeting. So I'll let you guys know how that's going to go. But anyway, just to kind of recap a little bit more on B trees. The whole purpose of a B tree. So let me go ahead and pick an example. Let me see. I guess the example is good enough. Yeah, sure. So the idea is that let's say we have a lot of nodes in every single, lot of keys in every single node. So let's say I want to find an element, but often whenever you're doing a database query in a database, often you're going to have to retrieve multiple records than just simply one record. So of course, for a binary search tree could be used to implement a database. And if you want to find some element, you could of course do a new search again and again and again. But for a B tree, it has all the keys, like let's say 15 and 20, it has keys that are kind of next to each other. So let's say if I found an element that I'm looking for, there's a good chance that elements that are next to it in that node could also be what we're looking for in our query. So the whole idea is that we could sort of retrieve all the keys in that one node if let's say we want to find multiple keys that are sort of close to each other, if you will. So the idea is that we don't have to do another search all over again if you want to find another key. We may need to, but we could just iterate through all the elements in each node and retrieve all of those as well, because there's a good chance that elements that are next to each other could also, maybe we're trying to also find those elements as well. So for database querying especially, it's a good chance that a lot of times we query a record, the other records are going to be next to each other that are similar to each other. Instead of having to do another search all over again, we can just go through all those elements in that node. So this is why it's kind of more of an improvement over an AVL tree, binary search tree, if we want to retrieve a lot of elements at one time. Now, of course, we could keep searching, keep doing find over and over again for AVL trees, but this is actually a bit more faster if we want to find multiple records at one time. So that's kind of the purpose of using a B tree. So that was sort of the insertion notes. So on Thursday, I'll do our midterm review. And I'll go over deletion next week, Tuesday. And of course, I guess that's it for today then. So I have no more to add for today. So there's no new assignment until after the midterm. So I guess take care for right now. Thanks for watching. Have a great rest of your day. And I'll see you guys on Thursday.